Okay, so let's get started today. We are finishing up classes today, and we only have a couple things to talk about with classes. One of them, we're going to be just quickly talking about what happens when you need to create a class only after you have read some information. So creating classes after reading info. And then we're going to talk about random shuffles. So for example, if you have a pack of cards, you can randomly shuffle it. But if you are implementing a card game on a computer, what might be a good shuffle algorithm for a computer? And that has to do with the example that Dr. Planck was doing with the rosters, where you want to randomly shuffle the pictures that appear in the table. And then we're going to start into hashing, which is the first data structure that you'll actually see in this course for organizing data, in which you'll be writing a lab on in Lab 4. So in his notes, Dr. Planck we'll go back to that roster problem, and he has the issue that, let's get down to it, we need to use a constructor to initialize the roster, okay? And so in this case, what he needs to know is the starting number for the image files. The problem is he's not going to know the starting number for the image files until he has done some verification on his input data. So I'm trying to get down to his thing here. So here it is. He is getting his starting number from, let's see, right there, from one of his command line arguments. Okay? So can someone tell me what the issue is? Because I've seen this code from you before. What if you just put roster R arg v2 up here? Okay, take this out. And in my declarations, I just put roster R arg v2. What might happen to my program? Doug?
Have an error because argv2 is a character.
So yes, if argv, so there's a couple. So I'm going to get, first of all, an error message because argv2 is a string. It's not an integer. So it's not going to compile. Okay, so I can't create it there. I have to first convert argv2 to a string. Okay, but Dr. Planck's point is that means that I'm going to have to wait before I create the class. I can't create the class until I've extracted the string from argv2. Let's say that this took a string, that the constructor took a string. Let's say the roster actually was taking the name of the print file that contained the names of the people in the class. So argv2 was actually the name of the file that contained the student names. There's still a problem here. Now what's the possible problem, Mark?
Not have a command line input.
Might not have a command line input. Maybe the user forgot to provide command line arguments, in which case I'm going to get a seg fault because there's not enough command line arguments. And this one I've seen in many programs thus far, which again is you're too trusting. You're assuming that the user has provided you legitimate input. But there's no guarantees that they have. They may have forgotten to provide command line arguments. So you can't use command line arguments before you have done checks on them to make sure that there's enough of them and that they have the right types and so on and so forth. So the point he's making in this part of his notes is that you have to defer the creation of the class until you have verified your arguments, and also in this case you have extracted the integer from the string. So his solution, which is to use something called a pointer, but we haven't discussed pointers yet, and we're not going to discuss them for another week and a half. And I actually think that I right now don't want you to have to worry about it. It's a totally new concept. So I'm actually going to, for the time being, skip over that. And he says roster 03 evil because he has a real aversion to your declaring variables in the middle of procedures, whereas I don't. Okay? I actually think it's an okay thing to do, although I think you need to be judicious. And in this case, I actually do think, in general, roster should be declared at the beginning of the procedure. However, I don't want to deal with pointers just yet. So there is a way to defer the creation of the class, which is you first do your argument checking and you do your extraction of the integer into the starting number. And then you belatedly declare the roster variable because now you have the starting number and it's okay to create an instance of a class. So for the next 2 weeks, this is fine to put off the creation of a class object until you have gotten the necessary information to create it. Now, when we get to pointers and go over pointers, which we'll do in a couple weeks, I'm no longer going to accept this solution. I, like Dr. Planck, will call it evil. Okay, but for the time being, I don't want to go into pointers. I think we really need to I think it gets confusing. There's some new syntax associated with pointers, and I think it's a diversion. So if in a lab we tell you in the next couple weeks before we get to pointers that you need to create a class object using a constructor and you don't have the information initially that you need because it has to be read from the user or because it's in command line arguments, then you can defer the creation of the object till you have that information. The way you do that, as you see here, is to move the declaration down. Is that clear? Okay. So that's point one. The next point is how do we come up with a random shuffle? Remember, our goal is to be able to read the names but then have them randomly appear in our table. We don't necessarily, if Alexander Blinn is the first name in the file, we don't want it necessarily to always appear at the first location in our table. We want to randomly shuffle the names. So if I gave you the names as cards, you probably would shuffle it like a pack of cards, right? You just shuffle them. But a computer can't do that. So the question is, what is a good shuffle algorithm? Okay, so what is a good shuffle algorithm? And Dr. Planck gives you 3 possibilities. Okay, possibility 1 is if I have n photos, so let's say I have n photos, then what he does n times is he says basically for I equals 1 to n, so I'm using pseudocode, generate a random number between 1 and n, output, so we'll call that R, okay, output the rth name slash photo. Okay, so maybe on the first iteration it generates a random number 5, and we can see if we look here that that refers to Landon Lockheed, so we'd output Landon Lockheed. Maybe on the second iteration we get the random number 12, which means we're going to output Brody Fairport. Okay, so that's a pretty simple algorithm. Generate a random number between 1 and n, output the rth name. What's the problem with this algorithm? This algorithm doesn't actually, well, it will work in that it will generate a table with, in this case, 18 photos. But can someone tell me what an issue is going to be? Doug.
You'll have repeats.
I may have repeats. Okay? What's to prevent me from generating, say, the random number 7 3 times? Nothing. So I'll end up in that case, if I generate the random number 7, I'll end up with William Grantee 3 times in my table. So if I generate 7 3 times, what must that mean about some other photo? Are all the photos going to be in there? No. If I've got a repeat, then it's impossible for all 18 photos to be in that table. Therefore, this first algorithm is flawed in that it's not even correct. It won't generate 18 random photos. There will be repeats. It's like if I tried to shuffle 52 cards, I would end up with several cards repeated, like the ace of diamonds might show up 4 times in my shuffle, and the 3 of clubs might never show up. That's no good. Okay? So algorithm 1 doesn't even work right. Okay, is that clear? It's not a good algorithm. Okay, so we take a second crack at it. Okay, we think, okay, that was an issue, so we think, this is what we do as computer scientists, think. Okay, think, okay, what if I create a table that is Booleans, and it indicates, I'll represent it with F's or T's, to indicates whether that photo has already been output. Okay, so initially I initialize that table to, or vector, to all false. Okay, because none of them have been output. So now I'm going to do the same thing that I did before. I'm going to say for I equals 1 to n, let R be a random number between 1 and n. Okay? Now what I'm going to do is I'm going to check to see whether that random number corresponds to a photo that I've already output. If it's not, I'll output the photo. Okay, so if R is 2, we see that that's false, so that picture has not yet been output. We will output it, and we'll change the F to a T. Okay? So basically, I might be thinking, okay, if, I'll say photos, if not, photos are, okay, so that means if the photos of R is false, then we output the photo. And we set photos of R to be true. Okay, but if it's not, that means we had already output that photo. So let's say after several photos had been output, that again, we come through here and we generate the random number 2. Well, now when we check it, we see, oh, we've already output that photo. So what we're going to do in this case is keep generating random numbers until we generate a random number that maps into a false entry in the array. Okay? So what I'm going to do is slightly change this from an if. I'm going to change, whoops. I'm going to say, okay, while photos of R. So while I am finding why I have a collision, that is, while I am finding a photo that's already been output, I'm going to generate a new random number. So I'm going to keep generating random numbers until I get one that doesn't map into a photo that I've already output. And when I come out of this while loop, I'm guaranteed to have an R that corresponds to a photo that has not yet been output. So I will output photo R, and I will set photos of R to be true. Okay, so this algorithm is going to work. Okay, it's guaranteed to work. Okay, the first time through, it will take only one random number, right? Because all of the no photos have yet been output. Okay. The second time through, do I have a pretty good chance of only having to generate one random number? What are my chances? Man in black, right there. I have 18 photos. Okay, the first time through, you can reason this out. You've had the math. Pardon? You have 18 photos.
There's 17 good ones, left to be 17 over 18.
Very good. So the second time through, I have a pretty good chance, 17 out of 18, of getting a unique number. Okay, after I've generated 2 photos, what's my probability of generating a unique random number? Come on. How many? 16 out of 18. Okay, but as I get more photos output, by the time I've output 17 of them, my odds have gone pretty bad, right? They're down to 1 in 18. There's only one random number left that I can generate that is going to correspond to a empty photo slot. So for those of you who know something about probability, by the time I'm down to the last photo, that is, I've generated 17 and I'm on the last iteration, so I have a 1 in 18 chance of getting a random number that matches it. What is the expected number of random numbers that I will generate before I will get that photo?
17.
It's actually, I think, 18. With it 1 and 18, I believe it's 18. So it's the chances are I'm going to have to generate 18 random numbers. So the problem with this algorithm is that it gets slower and slower as I have generated more images. So turns out that roughly speaking, the first, I may not be as bad as, actually I think it's 9. Is it really 18 or is it 9? Even there I'm a little, is half. Is the expected number 18? The expected number really may be 18. It may be 18. That just seems high. I'd have to think about it. Okay, at any rate, the idea is that this gets slow as we go along. So the question is, can we do better than that? Okay, because it's really bogging down at the end. And if it wasn't 18, but it was, say, 1,000 photos, then it's really going to slow down. Okay, so can we come up with something better? And the answer is yes. So Dr. Planck's solution is the following. His solution is, again, let's do a table. Okay, but what he's going to do is he's going to start at the end of the table with entry 17. And he's going to generate a random number between 0 and 17. And whatever number he generates, that's the photo he's going to output. Okay, so let's say, and initially he fills them with numbers like this. So this is unsorted. So initially, so what this array now indicates is the number of the photo we're going to output. Okay, so it's clearly not shuffled at this point. So his first step is the last number he's going to fill in first. So he's going to generate a random number. Let's say he gets 3. So what he says is, okay, I'm going to actually output photo 3 in the 17th location in the table. That is, in the last location in the table, I'm going to output photo 3, and he swaps 17 in here. So he does a swap. Okay, so 17 goes up to there. So now, the next step, he's going to generate a random number between 0 and 16. And you can see there's no chance that he's going to end up outputting 3 again, because 3 is sitting in location 17. So he's guaranteed when he generates this random number between 0 and 16 that he's going to get a unique photo. So let's say he again generates the random number 3. Darn, bad luck, 3, twice in a row. Darn it. Not so bad because 17 is now there. So we didn't end up duplicating the photo. We just put 17 there and do a swap. Now 16 goes into 3. See, not a problem anymore. We didn't end up with a duplicate photo because we had swapped 3 and 17. When we again generated the random number 3, we now put 17 in there. So now we've got the last 2 positions in our table set. So we're going to set up 15. So we generate another random number. Let's say it's 0. Okay, so we had 15 here, but now we put photo 0 there and move 15 up to here. So hopefully you see this is a nice algorithm. At each step, we are guaranteed to find a unique photo. Okay, a photo that has not been previously output. So, and we're only using a single random number at each step. That's great. One random number and we're guaranteed to find a unique photo. So this is a good algorithm. Okay, so this is basically for I equals n to 1, so we're counting down now. Okay, so we're going to generate r equals a random number between 1 and actually, now I'm going to, because I am dealing with an array, I'm going to go to the real thing. So it really is n minus 1 to 0. And I'm generating a random number between 0 and I. Okay? And then what we're going to do is swap contents of, we'll call this photos. So swap contents of photos R and photos I. And when we're done, we will have a random shuffle. Not only will we have a random shuffle, but at each step we'll have generated only one random number. So for the whole thing, we will have generated only n random numbers. That's pretty good. In fact, it's the best we can really do if we want a truly random shuffle. Okay, there's other ways to do a random shuffle, but this is, as it turns out, as good a way as any to generate a random shuffle. Okay? So are there questions about any of these three algorithms? So we went from, just to recap, we went from one that may seem intuitively obvious but doesn't even work. So this one has repetitions, repeats. So this one repeats photos, repeats some photos, and omits others. Okay, the next one works. Okay, so every photo appears once. But if I was going to do an analysis which would require some statistical work, I would find that roughly n squared random numbers must be generated. Okay, so this would require some statistical work that I don't want to do, but if you did it, you'd find that it would require roughly n squared random numbers. Okay, that's no good. Well, we can do better, as this last one showed, where we only required n random numbers. So this again is an example of thinking about it and not always taking the first solution that comes to mind. Okay, you may also think, well, how did you get this? I mean, that's great. You showed it to me. How do you think that I'm supposed to come up with that on my own? I don't. That's why I showed it to you. Okay? But the idea is, as I keep showing you these things, I call these tricks. These are tricks that as you get more and more tricks in your bag, then when you're attacking a problem, you can start reaching into your bag of tricks and say, does this trick work? Does this trick work? And eventually you find the trick that unlocks the problem. Okay, and as you get better and better at it, you will quickly start to see patterns where you know that certain tricks typically solve certain patterns well. Okay, so that's why we go through these things. Not because I think you should be able to do this on your own yet. I don't. Okay, in fact, when people, I'm sure the first person who thought of it didn't see it immediately. It took them a little bit of time, and then they're probably pretty thrilled when they found the cool solution. Okay, but it also is meant to show you that you can have efficient solutions and less efficient ones, that there's not always a single right answer. 2 and 3 both created a random shuffle, but 3 was a lot more efficient. Okay? So that's what we're kind of tackling in this course. It's not just showing you data structures or reviewing C++. We're also trying to teach you to be good problem solvers. And we're trying to give you some tricks or tools, if you will, that helps you to be good problem solvers. Okay? Okay. So moving on. Our first data structure of the course, hash tables. We're now officially done with our review of C++, and we're moving into pretty much completely new material. Okay, although of course it builds on C++. That's why we reviewed it for almost a month. Okay, so in 102, we showed you some search strategies, right? One of the big things we do in computer science is we want to be able to efficiently find things. That's Google's model, right? If you Google for something, you don't want to wait 10 hours for your answer. You want Google to come back very quickly with some search results. So finding information in a collection of data is one of the biggest tasks we perform in computer science. And in 102, we showed you a very efficient algorithm called binary search. Okay, can someone remind me what binary search does? In fact, man in kind of the pink right there. Do you remember binary search?
I think it's when you split the thing you're searching into two, and you keep doing that until you find what you want.
Very good. So the idea is, and do you remember what condition the elements in the array had to satisfy? There was an important condition in order to make this algorithm work. The values had to be arranged somehow.
Was it something like that to be even or odd?
It wasn't even or odd.
Pre-sorted.
Pre-sorted. Very good, Gerald. So it didn't work if they weren't pre-sorted. They had to be pre-sorted. Okay, so maybe like 23, 35, 42, 61, so on and so forth. And the idea was at each step you went for the middle element if your search, and you had a target, so let's say the target was 42. If the element you looked at in the array, the middle element matched 42, you were done. But otherwise, if it was less than the element, so in this case, let's say the middle element was 103, you'd search in the lower half, and if it was greater than 103, you would search in the upper half. So at each step, we threw away half the array. Okay? And does someone remember how many searches it required on average and in the worst case? How many probes? Sarah?
On average,
Half the entries? Okay, it does better than it. Okay, so Sarah's guess is n divided by 2. If there's n entries, it does better than n divided by 2. A lot better. That's the average, actually, if you were to use something called linear search, and it was in there. Anyone remember, if you keep having it, very good, log 2 of n. Okay, so if you keep having something every time, then the number of times that you can have it is log 2 of n. So this was very efficient, okay? But there's a couple problems with this. Okay, first of all, it's log 2n. It turns out that we can do better than log 2n on average. Okay, this isn't the best we can do. Wouldn't it be nice if on average we could find it with just a single access? Not log 2n, but a single access. Okay, people have turned their attention to, is this possible? The answer is yes. if you're willing to, well, we'll talk about it, but the answer is yes, on average you can do better. There's another issue here, which may not be apparent at first, but you're dealing with static data. What if I have a dynamic collection of search items, which is what Google deals with? Information's being constantly added to the web and constantly deleted. Google is not dealing with a static web. And this array is static. It has a fixed number of entries. So what happens if I have to start adding information to this array? Well, you could say, fine, don't use an array. Instead, why don't you use a vector? Because I seem to remember that you said a vector is dynamically resizable. And you would be right. So let's say, okay, I changed to a vector. At least I can now insert things. But let's say I need to insert 12 into this vector. That's not so good, is it? Because 12 needs to go into the very first entry. And the only way I can make that happen if I'm going to insert 12 is I have to move every other entry in the vector one down. That is, I'm going to have to move every entry. The only way I can do it is I'm going to have to move each entry one to the right. So I'm going to have to move n entries to the right just so that I can insert 12. That's really inefficient. Okay, that's horrible, in fact. Okay, so we have something that doesn't handle insertions very well. And the same thing with deletions. If I delete something, I'm going to have a hole in my vector, and I'm going to have to shift everything to the right of it to the left in order to close it up and not have a hole. And again, that's going to take a fair amount of time. So we have an algorithm that, first of all, while good, much better than linear search, isn't necessarily as good as we can do. And secondly, insertion and deletion is pretty expensive. Up to n entries may have to be shifted for a single insertion or deletion. So the question is, can we do better than that? And I have a shiny new car for you called hash tables that does just that. Okay? So our shiny new tool is going to have some nice features. I'm the salesman now. And I'm selling hash tables to you. And I'm saying, all right, so turns out that on average, okay, it takes one probe to determine if the target is in the table. That is, it doesn't matter whether the target is in the table or not in the table. On average, it takes only one probe. That's great. Not only that, on average, I can insert or delete a new element with one probe. Okay? That's pretty good. Okay, insert with one probe, and I'll say one data move. That's great. I've gone from log 2n to 1 on terms of probes, and on insert or delete, I can do it with a single probe and a one data move. Are we sold? I'm the salesman. I'm going to ram this down your throat. Okay? You spy it. Okay? So you take your shiny new creation home, and it occurs to you in this after the glow fades, wait a minute, that Dr. van der Zanden was a pretty slick salesman. He had some hair gel in there, and he was talking pretty fast, and he looked pretty smug when he got my $5,000. Was there something I should have known about that hash table? I mean, if something's too good to be true, sometimes it is. So turns out that, yeah, we got to give up some things. Okay? We had some nice, we have to bend some things and give up some things. So I was slippery. I said, on average, it takes one probe. Okay? I didn't tell you the worst case. Okay? The worst case with binary search is also log 2n. So with binary search, both the average and the worst case is log 2n. Okay? I didn't tell you the worst case. Worst case with hash tables, okay, in the worst case, it takes n probes to determine if the target is in the table. And for insert and delete, in the worst case, it also takes n probes. Although the good news is there's still only one data move. Although still only one data move. I didn't lie there. I didn't exactly lie, I just omitted some crucial information. Okay, and then there's another feature that I give up, which you may or may not care about. Sometimes we do, sometimes we don't. Okay, we give up the guarantee that the data is ordered. Now, the data is no longer ordered. Okay, which you may, sometimes it's useful if you want to go through and print out like a phone book. It's useful because it's already in alphabetical order, whereas with hash tables, if at the end for some reason you need it in alphabetical order, it won't be in alphabetical order. So it no longer keeps the data in sorted order. Okay, so here's a classic use of hash tables, showing their advantage and disadvantage. So a classic use of it is you have a corpus of data, and you want to count word frequencies. You want to know how many times the word the appears in the corpus. You want to know how many times the word Brad appears in the corpus. You want to know how many times the word Spot appears in the corpus. So you want to count word frequencies. And then at the end, you want to print the words out in, say, alphabetical order along with their word frequencies. So a hash table is very good for the first part, counting the word frequencies, because what you do is you simply, for each, you have pairs. So hash tables keep what is called key value pairs. So in this case, the key is the word, and the value is its frequency. So basically, you go through each word in the corpus, and if the word already is in the hash table, you increment the frequency by 1. If it's not yet in the hash table, you add it to the hash table and set its frequency to 1. Okay, so it's a pretty simple algorithm. For each, I'm not going to write it down, but for each word, if the word's already in the hash table, increment its frequency by 1, else insert it into the hash table and set its frequency to 1. So that's well and good. That makes it, basically, on average, we'll be able to do this with n probes. But now we have to print the words out in sorted order. Well, the data is no longer in sorted order, so at the end we end up having to sort it. Okay, whereas if we'd use some algorithm that keeps the data in sorted order, we wouldn't have had to do that. Okay. Later in the course, we will talk about a data structure, trees, that allows you to keep the data in sorted order. But it handles insertions and deletions gracefully, unlike arrays. Okay, so we will talk about such a data structure, but it turns out if we want to keep the information in sorted order, we have to give up on our average of 1 for expected number of probes. We'll have to drop back to log 2 of n. So there's trade-offs. Okay, always trade-offs. Okay, so with hash tables, that's what we're concentrating on now. We know what its advantages and disadvantages are. In designing a hash table, obviously, we want to try to minimize the chance that we encounter the worst case. So in doing it, we will try to minimize this possibility of running into the worst case and maximize the possibility of getting that good average case performance. Okay, so I first have to tell you what is a hash table. Okay, so a hash table is a number of things. So we have typically a vector, okay, of some size. A vector, which we call a table, of some size. I'll call it n. And I'll call it t. So a table of size t. And we have something called a hash function. That maps keys to the range 0 to t minus 1. So we have a hash function, hash, takes a key, and it produces a number between 0 and t minus 1. And that number will be our, what we use as our probe into the vector. So what we're hoping is that when we make our probe, if we're doing an insert, that that entry in the table is empty. Okay, we're hoping it's empty so that we don't have to do anything other than insert it. So let's take a very simple example. In fact, let's use Dr. Planck's because he's already got it for us. Okay, so he has a table of size 10, and let's say he's going to put Luther in. And let's say that hash of Luther is equal to 1. Then we put Luther into entry 1. Okay? Let's say we now do a hash on Rosalita, and we get that her hash is 4. So we put Rosalita into 4, and now we do Binky, and Binky hashes to location 2. Okay? Well, just like with those photos earlier, remember that algorithm 1 where I generated random numbers and that was the photo I output? My luck eventually ran out, right? Eventually, I got a duplicate. Well, our luck will eventually run out with hashing too. Let's say that our next one to insert is D'Antonio, and let's say that its hash value is 1. That collides with Luther. Luther, that spot is already occupied. So now you can see what the worst case might be. The worst case may be that we keep trying to insert and we keep finding entries that are full, that are already occupied. So our third thing is that we have to have is what's called a collision resolution strategy. Okay, what to do? Okay, so what to do when we want to insert, when we try to insert a key and its target location is occupied. Okay, so it's important to have a good collision resolution strategy because we don't want to have to search too many of these entries in the hash table. We hope that very quickly we can find an empty position. Okay, Doug?
So the hash function for this particular example
Was not, right.
is hash value modulo 10.
Yes, so in fact, typically what happens, I was going to get to that. So in fact, if you looked at the hash values, it was generating numbers much greater than if you look at the hash values, here we go. They're actually much greater than the table size. So typically what's actually happening is that our hash is really some function f of key, and then we mod it with t. Okay, remember I told you you've got to get used to mod being your friend because we use it a lot. Okay, so usually you take some function f, apply it to the key, and then you mod it with your table size. Now, can someone tell me what is a very desirable property of the hash function? What is it going to have to be able to do if we want our probes on average to just take one probe? Okay, I'll help you out. What if I let f of key equals 0? Is that a very good hash function? Always returns 0 no matter what. You think that's a good hash function? Think I'm going to get average of one probe? No. And what's your name? With the Tennessee, Jerry?
Yeah, Jared.
Jared. What do you think is going to happen very quickly?
You'd have to search every spot.
Right. Very quickly, everything's going to be going into 0. Everything's piling into 0. We can't really expect to have an average case of 1 if everyone wants to occupy slot 0. So what does my function need to do? Obviously, setting it to 0 isn't a very good strategy. In some sense, what does it have to do with the keys? Come on, one person should have read the notes. What? Well, it doesn't have to be exactly bijective because here you may have all these ones are going to end up, they're going to be collisions, right? Because the last number is going to end up, there's duplicates there. So it's not exactly bijective. Jeremy, you had a good guess, but.
I was gonna say you wanted to try and make it so that it would give different values for
Different values, you're right, but those different values need to be, there's a word I'm looking for. Not unique, because they're not here, as I said. These values, you'd like them to be unique, but it turns out that's too strong of a thing. Just like with random numbers, you can't guarantee that they're going to be unique. Evenly distributed, very good. We want the hash function to evenly distribute the keys. So every bucket, so we often call each, and you'll hear me refer to these entries as buckets, because that's how I was taught. I was taught to think of these entries as buckets. Okay? So you'll hear me often refer to them as buckets. We want our hash function to basically, with equal probability, assign a key to any of the buckets. So it needs to be uniformly distributed. So a desirable feature of a hash function, so for the hash function, okay, desirable property is that it evenly or uniformly distributes the keys. It doesn't mean that you're going to avoid collisions, but it means that you're not going to always be piling into the same entry. So uniformly distributes keys over the buckets. Okay, and obviously with the collision resolution strategy, you would want there to be some niceness to it too. So I'm actually going to slightly reverse what Dr. Planck did, because you're going to start doing some of this hashing in lab tomorrow. So I want to hit on, I have about 15 minutes, and I want to hit on a couple of the very simple collision resolution strategies and a very simple hash function. And then we will go into some more complicated hash functions and some more complicated collision resolution strategies on Thursday. So with collision resolution, there are two very simple strategies. Okay, one is called separate chaining, and one is called linear probing. And I'll just quickly again go to Dr. Planck's notes. Before I define them, I'll just illustrate it. Actually, I don't think he has okay, he doesn't actually show it, so I will. So what happens with separate chaining is that each bucket actually has a vector associated with it. So if this is our hash table, this is our entries, each one has a vector associated with it. And every time a key hashes in there, so let's say Luther, so we'll start out and all the vectors are empty. So Luther hashed to location 1, so we push Luther onto this vector. Then Rosalita went into entry 4, I believe. So we push Rosalita onto that vector. Binky went into 2, so we push Binky there. And then D'Antonio hashed into 1. So that's a collision, but we don't care. We just add D'Antonio to the vector for bucket 1. So separate chaining is very simple. You just have a vector associated with each bucket, and as you add entries to the hash table, you simply add the key to the end of whichever bucket's vector it hashes to. Okay, so separate chaining, we simply keep a vector. Every bucket has a vector. Okay, and just add new key to end of appropriate buckets vector. Okay, so that's a pretty easy strategy, right? So can someone tell me how many entries, what's the maximum number of entries that we can have in our table, the maximum number of keys, and expect to have roughly on average one probe for a search? Just intuitively. 2? So if I have 2, that means only 2 of the 9 entries or 10 entries there are occupied. Remember, the hash function uniformly distributes things. N, very good. Or in this case, since I said the table size was T. Because if it's uniformly distributing them, you would expect on average that once you have T keys, since the hash function is uniformly distributing them, then the expected value is that each bucket has one key. Okay, now we know that that's not absolutely true. Due to collisions, there's going to be some buckets that are going to have multiple keys, but the expected value is 1. Okay, so we don't want to go above, if possible, 1. And we define an important term called the load factor. Okay, and the load factor is simply the number of entries or number of keys divided by the table size. So it's a fraction. And we need, for separate chaining, for that load factor to be less than 1 in order for the expected number of probes to be 1. Okay, so with separate chaining, if the load factor is less than 1, then for separate chaining, the average insert, delete, or find takes 1 probe. And by probe in this case we mean how many entries you search. Now some of them, like if I try to find D'Antonio here, it's 2 probes, because I'll have to do a linear search. So what happens with separate chaining is for a find, we calculate the keys bucket, and then we do a linear search through the vector. So if we're looking for D'Antonio, we calculate the key, it's 1, or the bucket, which is 1, and then we have to do a linear search. D'Antonio actually requires 2 probes. So each entry in a vector that we have to look at is considered a probe. But as long as we keep the load factor less than 1, then for separate chaining, on average our inserts, our deletes, and our finds will take 1 probe. Now I said the worst case was n. In the absolute worst case, I could choose T keys that all hashed to the same entry. Really bad luck. The chances of that happening with a good hash function are vanishingly small. Okay, just like if I choose a card from a well-shuffled deck, it's going to be really improbable that, say, I select the ace of diamonds 20 straight times, right? Or 10 straight times. Really? You wouldn't expect that. Okay, if I was to give you a pack of cards, well shuffled, and I told you to select a card, and I offered you a bet, I would say the bet was, I don't think that you can select an ace of diamond 10 consecutive times. And I'll give you even odds. Okay? So you win if you select the ace of diamonds 10 consecutive times. I win if you don't. Anyone going to take that bet with me? Come on. Few suckers. Barnum said there was one born every day. None? No takers? All right. How much is your bank account worth? Oh, darn it, not getting rich on that bet. Okay, so none of you took that bet, right? Because you realize that in a well-shuffled deck, the chances of drawing the ace of diamonds is what on a single draw? 1 in 52. Okay, if you know your probabilities, you know that the chances of me drawing an ace of diamonds 10 consecutive times is 1 divided by 52 to the 10th power. Okay? Yeah, it can happen. I'm not sure that, I think that probability is actually worse than my probability of winning Powerball, which is already pretty minuscule. Okay? So I'm guessing that that's less than 1 in 200 million. I think chances of winning Powerball are like 1 in 180 million or something. At any rate, my point is that the chances, if my hash function uniformly distributes the keys, it is incredibly unlikely. I mean, it would be absolutely horrendous luck if all 10 keys hash to the same bucket. Okay, so yes, in the absolute worst case, all 10 keys would hash to the same bucket, and I would have a vector that was 10 entries long, and it would take me on order 10 keys to find stuff. But the chances of that ever happening with a well-distributed hash function are vanishingly small. So the chances that the worst case, just a moment, Alan, the chances that the worst case actually happens, I didn't lie that badly when I was my fast-talking salesman. As long as I gave you, quote, a good engine, then the worst case is unlikely. Okay? Yes, Alan?
The load factor has to be a lot less than 1 for the average.
Not for separate chaining. For linear probing, yes. Not for separate chaining.
It's like 0.99 or something, then
For linear, Alan, you're talking about open addressing and linear probing.
I don't think
Yes, you are. For separate chaining, which are,
Are you calling it a probe if you have to, go down the chain?
yes.
So if you go down the chain twice, that's 2 probes?
Mm-hmm.
Okay.
So if I have 10, if my hash table is 10 entries, okay, and I have 10 keys,
Yeah.
and a well-distributed hash function, okay, on average, each bucket is only going to have 1 entry,
Okay, I'll go with that.
okay? Now, if it's open addressing the other 3 schemes, then yes, the load factor can't get much beyond 50% before we start going through the roof. Okay, so you're right. But separate, this one strategy, in my opinion, the best one, is because of this. The load factor can get very high without it being an issue. Okay. Okay, so the other strategy is that you're going to be actually doing in the lab tomorrow is linear probing. So in linear probing, see if Dr. Planck shows that one. Yes. So here, with linear probing, the first 3 entries go in as before because there was no collisions. The 4th one was D'Antonio, and it collided. So what you do with linear probing is you start a linear search at the bucket where the collision occurred, and you perform a linear search until you find an empty entry, which occurs at location 3, and you put the value or the key into the first empty entry that you find. Okay, so now if I added some more, let's say I added, do we have any more? Yes, so now he added Frenchie, and Frenchie hashed to location 2, so he starts a linear search, and the first available spot is 5, so he puts Frenchie into location 5. Yes?
Are the empty entries going to have say a Boolean value of 0? So I can say if entry something, then go on to next entry.
So, good question. The question is, if the entry is empty, how do you represent the fact that it's empty? Typically, what you do is you choose, so this is storing strings. It's not choosing a Boolean, so I can't put a Boolean in here. So I would choose a value that I don't think can ever be inserted, which in this case is an empty string. I don't ever expect to put an empty string as a key. So I would initialize initially all of my entries to the empty string. Okay, so that's how I would be able to detect a empty entry. If it was an integer, if I was storing integer keys and the integers all had to be positive, I could use -1. Okay, now if I can't find a value that is guaranteed to never occur, I could create a second vector of Booleans like you suggested. And then in that vector, I would keep true, false. Okay, so the best case is I can find a value that will never occur and initialize my entire hash table to that value. Worst case, I can't do that. I have to create a second vector that's Booleans like you suggest. Okay, so linear probing is to find the first empty spot using linear search. So if I do that, can anyone, just a second, Doug, back here, can anyone in this hash table, how do I determine that D'Antonio is not in the vector? At what point can I stop searching? Do I have to search the entire vector, all 10 entries, if I have D'Antonio, or can I stop earlier? I can stop at 3. Very good, Doug. So with linear probing on finding, I can stop as soon as I reach an empty entry because it's guaranteed. Now, you can say, wait a minute, what if you delete? We'll cover that case. Right now, we're assuming no deletions. So if we assume no deletions, as soon as we reach an empty spot, we know for a fact that D'Antonio could not be in there because if D'Antonio were in the vector, then we would have chosen location 3, right? We would have chosen the first empty spot. So linear probing, we'll just finish up here. Linear probing, okay, inserts. We find the bucket to which the key hashes. And do a linear search to find first empty entry, which we hope in most cases is the actual bucket itself. And with finds, okay, we find the bucket to which the key hashes. And do a linear search. Until we find the key. Or we find an empty entry, in which case the key is not in the hash table. Okay? So tomorrow you will start in on hashing with Lab 4, and you'll get a little bit of information also in the lab about computing a hash function. And then on Thursday, we're going to consider some more complicated collision resolution strategies, a couple hash functions, and we'll talk about how linear probing is not, how it degrades more quickly as the hash table fills up.